This section, we will solve partial differential equations using separation of variables. However, this is not going to be the exact separation of variables we learned at the beginning of the semester. It has some sort of it, but not with a little twist in here. All right, well, when do we use this method of solution? So the equations, for instance, that we solved in the previous lecture, in the last section, previous sections, those equations contain one partial derivative term of any order at a time, like the partial derivative with respect x or respect y, but it was only one at a time. Well, in this case, for this kind of partial differential equations with more than one partial derivative term having differentiating with respect to different variables, not with respect to the same variable, we need a special case of separation of variables. So here we go. Number one, we're going to start by assuming a solution of the form u of x y equals a product function, the product between a function of x and a function of y. But, or in any other cases, like the ones that we may see later, it can also be a function of x and a function of time, a function of t. Well, speaking about time, well, when do we solve this kind of equation? Because it turns out that many situations in nature can be modeled using partial differential equations, and oftentimes those phenomena are described not only in terms of space but also in terms of time. Like in this case, we have a factor of space, that is the one-dimensional space, and the time factor, that is the function of t, right? Of course, we can increase the dimensions, work with um, what's it called, with in the two-dimensional space along with time, in the three-dimensional space along with time. That's actually technically four variables at the same time, but well, that's too advanced for this course, right? For those, take actually the course partial differential equations at a four-year college. Not so that's not anything we're going to do here. All right. Even the second order, when we go two-dimensional, those get intersect, right? Well, so we're going to assume a solution of that form, f of x, f of x times u of y, or f of x times u of t. And then we're going to differentiate this assumed solution as needed and substitute into the PDE. We'll see about it. We're going to separate the variables f and g. And then once we separate those variables, we're going to introduce what we call a separation constant. This is the plot twist in comparison with the separation of variables that you already know from week one. All right. So, and so since that expression involving x will be equal to the expression involving y or t, both sides must be equal to that constant we're going to introduce. And that constant we often use is the constant k. All right. So what we did in the previous step, we'll formulate to separate ordinary differential equations, solve them with all of the methods that you know from the entire semester. Most of the time, separation of variables. I mean, spoiler alert, right? And then once we solve these ODEs independently, then we're going to come up with a solution that will be the product of those two functions we obtain separately. All right, so, and of course, for initial value problems, well, you'll see how they work. All right, so um, let's see. So let's solve partial of u with respect x equals to partial of u with respect y. All right, so we're going to assume a solution of the form u of x y. That is because we have everything with the dependent variable u changing with respect x and with respect y. So we're going to assume a solution as a product of a function of x and a function of y. All right. And we're going to take as many derivatives as required. All right. So guys, to shorten the notation, I'm not going to use the parentheses x and the parentheses y. This point should be safely assumed that f is a function of x and g is a function of the other variable, y or t, depending on what we have. All right. And that's just so I don't have too many parentheses and so we don't write that much. So from here, I'm going to take the partial of u with respect x. So here f changes, so that becomes f prime. But because g is constant when differentiating with respect x, that just remains g. That doesn't change. Also, we need to find the partial of u with respect y. And well, in this case, differentiating with respect y, f remains constant. So that's f times the derivative of g, which is g prime. All right. And we have everything we need to substitute into the PDE. All right. That is the partial of u with respect x is going to be substituted here, and the partial derivative with respect y is going to be substituted into the right hand side of the PDE. All right. And so substituting gives us f prime g equals to f g prime. How do we separate the variables? Throughout all these exercises, the trick here is to divide both sides by fg, right? Divide both sides by fg. Well, on the left-hand side, the g's cancel, and that leaves us with f prime over f. On the right-hand side, the f cancels, and that leaves us with g prime over g. Right? Do you see how we separated the variables? We have all f's on the left-hand side and all the g's on the right-hand side. Here is where we introduce the separation constant. So these two should be equal to a separation constant. We're going to call it k. All right? What are we going to do? We're going to set the f equation equal to k and the g equation also equal to k. All right? So we're going to solve these two separately and independently. So I'm going to do f prime over f equals to k. All right? Notice how we're using the prime notation, that is the short notation. But when we solve the two equations, I'm going to go back and use the Leibniz notation. So this f in the denominator really means 1 over f, and f prime means df dx. And if you're wondering why df dx, again, keep in mind that f is a function that depends on x. All right? That's why df dx. And let that be equal to k. Okay? Now, let's separate. Okay, this is a separable equation, right? So, move the dx to the right-hand side, and we're going to be left with df over f on the left equals to k dx. Integrate on both sides. ln of f on the left equals to kx plus some constant of integration that I'm going to call c for now. But our goal is to solve for x, so how about exponentiate both sides on the base e, so we can cancel e with ln, and f equals to e to the kx. But guys, what is e to the c? Remember, isn't that just another c by absorption? We did that many times, right? So that's simply a c in the front. So we already have the f factor. Let's have a look at the g factor, right? The g function. Well, we're going to set g prime over g now equal to k. All right. So we did 1 right here. Now let's do 2. Okay. So number 1, number 2, g prime over g equals to k. And guys, this equation really looks exactly like the one we solved, right? Except it's a variable, it's a function g, and it also depends on y this time. But I'm gonna do it anyway. I'm gonna do it. I mean, it doesn't hurt. So that's 1 over g dg. But keep in mind that g is a function of y, right? So dg dy equals to k dy. So let's multiply both sides by dy. Oh, wait, no dy here, just k. Let's multiply both sides by dy. That's going to leave us with dg over g equals to k dy. All right. And let's integrate both sides. Okay. So that's going to leave us with ln of g equals to k dy. I mean ky. But in this case, plus another constant. But we can't use the same constant we already used in the same separation. So in the previous separation, I'm just going to use another letter, d. And well, similarly as in the previous solution, exponentiate both sides. E to the ln, right? E to the ln cancel out. G equals to, again, e to the d is simply another d, e to the ky. All right? So we just obtained the two functions whose product are going to comprise the general solution to this partial differential equation. All right, well, so let's see. Let's move to the next page. I have some space at the top of the next page and write the general solution. So u of x, y equals to, again, let me state the form of the solution, f of x, g of y. So u of x, y equals to f, which is c e to the kx, d e to the ky, right? There's a couple of things we might want to do. Number one, multiplying that c times a d, that is a constant times another constant, that's just going to give us another constant. Well, I'm just going to write that as an a. So that's a, and then e to the same base, right? What do we do with the exponents? Add them together. Mm-hmm. Kx plus ky, right? And that is our general solution, right? That's the general solution to the PDE. All right. Now, how do we find the particular solution? Well, so to find a particular solution, we would need an initial condition. We would need a condition. And actually, that's given with the problem, isn't it? So in this case, with the condition u of 0 y equals to e to the 6e to the 2y. So let me do that on the side. So with u of 0 y equals 6e to the 2y, that is, let's evaluate u of 0 y into the general solution. That is, u of 0 y equals to a e to the kx plus ky, but y, wait, x actually is a 0 here, right? Ky, right? Well, so the right hand side becomes a e to the ky, and what's u of 0 y? That's whatever in the initial condition is given, which is 6 e to the 2y, all right? Okay, so we're going to use these to essentially equate coefficients like undetermined coefficients, remember? In a similar way, that's how we're going to get A and K. So all we're going to do, let me highlight 6 equals to A and 2 equals to K. All right, how about that? So A equals to 6 and k equals to 2. So we may go back to the general solution and call it finally a particular solution. So this is general solution, and this is u of x y equals to a, which is 6 e to the k. Okay, that's k equals to 2x plus 2y, right? Final answer. This is particular solution, right? So that is our first example of solving a PDE using the method of separation of variables. Okay, guys, let's do a follow-up to this example. So example number two is essentially example number one with a little twist. So solve the equation in example one, subject to the condition in a similar way. However, this one has two exponential terms. So the purpose of this follow-up exercise is to show you how do we handle this type of solution when our initial condition has more than one term. All right, let me show you. So number one, again, the general solution of the previous example, which is u of x y equals to a e to the kx plus ky. Again, evaluate u of 0 y. That is, replace every instance of x with 0. That is a e to the k times 0 plus ky. All right. So that's going to leave us with a e to the ky in a similar way equals to u of 0y. But notice in this case, this one has two different terms, right? So that is 2 e to the, what is that? Negative y plus 3 e to the negative 2y. All right? 3 e to the negative y, 3 plus 3 e to the negative 2y. All right? But wait a minute, guys. Do you see the problem here? We only have one exponential term on the right and two on the left, right? So what do we do in a situation like this? Well, okay, just bring another term. How about call this b e to the k? However, do you see that the coefficients of y on the left hand side of the equation they're different? So that's why you might want to label this as a k1 and a k2 over here. All right, and only then just equate coefficients again. All right, so that is a equals to 2. B equals to 3. All right. What else? What do I have? K1 equals to the coefficient on first exponential, that is negative 1. And yeah, that one. K2 equals to negative 2. Right. Let me write those down first. So A equals to, what is that? A equals to 2. B equals to 3. K1 equals to negative 1 and K2 equals to negative 2. All right. And then we can form our particular solution, which will be u to the u of x y equals to, okay, in general, what do we have? A e to the k1 x plus k1 y plus b e to the k2 x plus k2 y, which is, in this case, just substitute a equals to 2 e to the k1, which is negative x minus y, plus b, which is 3 e to the negative 2x minus 2y. Final answer. All right? So that's what we do when we have two exponential terms. Or three, if you happen to end up with three, just add one more. C e to the k3y. If you had more, d e to the k4y or whatever. All right? So just extend to how many are needed. All right. So let's do one more exercise, one that it's even more involved. All right? So what do we have? Okay. X ln of x times the partial of u with respect x plus t times the partial of u with respect t equals to 0, subject to the condition u of x1 equals to 4 ln of x to the second power. All right, let's have a look at this exercise. So number one, again, we're going to assume a solution of the form u of xy equals to, oh wait, we're not xy. In this case, we have t, right? So which is a function of x times a function of t, right? And let's take the necessary partial derivatives as required. That is the partial of u with respect x, which is the partial of f, well, the derivative of f, if f is f prime, times g, which remains constant, and the partial of u with respect t, so f remains constant, and g becomes g prime, right? Into the PDE. So x ln x f prime g, right? Again, if it works for you, so let me box this with different colors and substitute this here, and let me box this one if it works. Oh, come on. And substitute there. All right. And plus t f g prime, and let that be equal to 0. Right. To begin our separation of the variables, again, we're going to use the same trick we did in the previous example. All right. That is, divide both sides by the product FG. Right. Divide by FG. All right. So that's going to leave us with x ln x. The g's are going to cancel here, leaving us with f prime over f. And here, the f's cancel, leaving us with plus t g prime over g equals to 0 over fg, which equals to 0. And we're almost there, actually, with separation of the equation of the variables, really. All we need to do is move the tg prime over g to the right-hand side. That's going to leave us with x ln x, f prime over f equals to negative t g prime over g. And well, do you see how we separated the variables? F's, which are functions of x, and g's, which are functions of t on the other side. So we're going to use a separation constant here. Let's call it k. All right. All right. So let's solve the two equations separately. Okay. So I'm going to do x ln x times f prime over f equals to k. All right, guys. Just a little bit of vocabulary here when we're solving this type of equations. If you ever take an upper division course that includes partial differential equations, whether in a mathematics course or in an engineering course containing solutions of PDEs, you may see something like this. Notice in this case, x is whatever is related to the dimension, to the space. So typically we call this the spatial equation. So we're going to solve the equation for the space, all right? Well, in this case, it's only the one-dimensional space. I know when you hear the word space, you think of the three-dimensional space, like in multivariate calculus, like in calculus. No, spaces can be one-dimensional, two-dimensional, n-dimensional. All right. So I'm going to move all the x's to the right-hand side. That's going to leave us with this f in the denominator. This is the same as saying 1 over f, and this f prime is the same as saying df dx. Again, because f is a function of x. And this is equal to k over x ln x. All right? Keep separating the variables to get df over f equals to k over x ln x dx. Integrate both sides, right? Integrate both sides. df over f equals to ln of f. What about the integral on the right-hand side? The integral of k over x ln x. How about a u substitution? Do you see it? Let me do that on the side right here. So u equals to ln x, du equals to 1 over x dx. So this will be dx over x, which is our du. Okay, so that equals the integral of k du over u. And let me continue up here, right? Running out of space right there. And that's going to leave us with ln f equals to the integral of du over u. Isn't that ln? K ln of u plus some constant of integration c. So we need to back substitute for u. What do we do? ln x, right? ln f k ln of, careful, we're going to have nested logarithms, right? ln x plus c. So let's now solve for f. Let's solve for f. So that is by exponentiating both sides by the base e. Okay. So guys, while we can cancel e with ln on the left-hand side, we cannot do it on the right-hand side, right? That's because of the coefficient multiplying with the ln. We could cancel them out, but first, have the coefficient go to the exponent of the argument. And in this case, the argument is the ln x in the inside of the other ln. So doing the basketball here, basketball for the coefficient, that's f equals to, what is that? E to the ln of x quantity to the k power. And well, what about e to the c? That e to the c, okay, will be simply another constant c, right? Let me do the plus c here, and then c, e to the, or no more ln. So actually we can cancel e with ln, and this is ln of x to the k, all right? So that's the first factor in the solution to the PDE. Let's have a look at the second one. That is by solving the second equation. So we gave the name of special equation to the equation containing the variables that relate a dimension x, y, or z, in this case x. How do we call the second equation? Well, because that deals with the variable t, which typically is the variable we use for time, we call this the temporal equation. Not that it really matters space and time, really. We're just solving equations. We're not applying this to any physical context. But again, if you ever get to see anything like this is the vocabulary you're gonna get to see. All right. Okay. So that is t prime over g equals to k. All right. Again, how do we do that? Well, first we did that equals to k. That's a number one. And then let's do this one. That's number two. Okay, so that's okay. I'm gonna divide both sides by t. That's gonna leave us with k over t, and this g in the denominator is the same as saying 1 over g times g prime, which is a really, yes. So yes, this is supposed to be a negative and then negative. Yes, thank you. df, oh wait, not f, dg dt. Again, this is a variable g that's a function of t. All right. So let's keep separating the variables to leave us with dg over g equals negative k over t dt. Right. And we can integrate both sides at this point. Right. And the integral of dg over g, that's going to be ln of g equals to negative k ln of t plus another constant of integration, namely have about d. We already used c. Let's just use another one, d. All right. Exponentiate both sides on the base e. Okay. That is g equals to e to the, oh, can we cancel e with ln over here? Again, not yet. So first, let's basketball the negative k and make it the exponent of the argument of ln, which is the t in this case. And again, e to the d, isn't that just another d? E to the negative, oh, wait, e to the ln of t to the negative k, which becomes g equals d. Now cancel e with ln, and this is t to the negative k. All right. I know we can move it down to the denominator with negative exponent, but I'm going to leave it like this for now. All right. So at this point, let me add another page. You guys might want to do the back side of the page. So now we have the two functions that comprise the general solution to the PDE. All right. Let's write that down again. To remind us of what we are looking for, we're looking for a function u of xt that is a product of a function of x and a function of g. All right, that is equal to c c ln of x to the k power d t to the negative k. And well, again, by absorption, we can multiply a times d. U of x t equals to c times d. That's simply a ln of x to the k power equals, times t to the negative k. So guys, that's our general solution to the PDE. Of course, we want to find a particular solution with some specific value for k and for some specific value of a. All right. Okay. So what did they give us for initial condition? U of x1. Okay. They gave us this time u of x1 equals to 4 ln of x to the second power. All right. Let's use that as a condition to get a particular solution. Okay. So with u of x1 equals to 4 ln of x to the third power. What are we going to do? Evaluate u of x1 into
Should be squared.
squared. Oh, yes, it's squared. Thank you, thank you. Right? Thank you. So evaluate u of x1 into the general solution. That is, every instance of t, replace it with a 1. All right? So that's going to leave us with, I'm going to leave us with 4, wait, not 4, that's a ln of x to the k power times 1 to the negative k power. Well, 1 to the negative power is just 1, right? The negative k power is just going to be 1. But what's u of x1? Isn't that for ln x raised to the second power, which is a? And here 1 to the negative k is simply 1. That leaves us with a ln x to the k power. Do you see the form on both sides? We can equate coefficients and exponents in a similar way we have been doing. That means we can set a equals to 4, of course, and k equals to 2. So a equals to 4, k equals to 2. So this is the general solution. Let's write down u of xc equals to a, which is 4, okay, ln of x to the second power, t to the negative 2 power. And that's our particular solution. And at this point, you might want to write this in the denominator with positive exponent. For ln x squared over t squared. Final answer.